like we know what we're doing here. Thank you very much. Okay, Andrew, you're on.
Okay. Back last fall sometime or last winter early, Dave asked me if I would like to do a talk on coaxial cable. And I said I would and would put it up for the beautiful weather that we would have at our May meeting. So here's our beautiful weather.
Welcome to spring.
And welcome to March. So the title is questions asked, questions answered, hopefully. So those would be, what is coaxial cable for the novice who's never seen it or doesn't know what it is? If open line is better, why use the coaxial cable? What is this thing called characteristic impedance? And that's going to be one of the major topics where I'm going to dwell pretty heavily on. What is velocity factor all about? How about minimum bending radius? And what about UV resistance and direct burial? I left the direct burial off, but we're going to talk about direct burial. All right, Frank.
Let's see if I'm doing this right. Well, there we go.
You missed one. You went two. Okay, so for those of you who are new to the hobby and new to this, or not familiar with the science, and perhaps some of you who are, what is coaxial cable? Well, simply put, coaxial cable is a multi-conductor cable where both conductors share the same longitudinal axis. Okay, hence the term coaxial. Next. The only geometry that can support that definition is in the previous slide is that one conductor surrounds the other. So you've got an annular outside conductor and you got a center conductor sharing the same long axis of the cable. Usually the outer conductor has an annular or circular cross section as shown in the next slide. We'll see that in the picture. And on rare and special occasions, you might find square or elliptical, but that's not manufactured. Those are usually custom designed. I worked in the induction heating business, and on occasion we had to build coaxial conductors out of copper, bus bar and stuff that had strange cross sections to them. Okay, next. So here's what, back again to the cable. What is coaxial cable? There it is. Those of you who have seen it know what it is. You've got an interconductor separated by a resistance or a high resistance insulation or dielectric material coated with a woven copper mesh and then with a plastic or vinyl or neoprene or some other rubber exterior insulation. And okay, hit that again there, Frank.
Hold on, I'm getting a picture of this. I like that formula for some reason or the other. It excites me.
So remember this equation, we'll get back to it later. ZO is 138 over the square root of K times the log of D1 over D2. D1 and D2 are now being hidden by the pictures up there on the screen. You can't see that, but we'll get to it.
Oh, wait a minute. Let me try something here. Hold on. There.
Okay. So there's D1 is the inside diameter of the outer conductor, and D2 is the outside diameter of the inner conductor. Okay, Frank. Some say ladder line or twin lead is a superior feed line, so why use coax? Okay, well, you get fantastic shielding, and we're going to talk about that. Due to proximity effect and skin effect, the signal on the coax is contained almost entirely between the two conductors and does not radiate in space. Unless, of course, you have bad things that you're doing with it. And like the, what's his name from Palomar Engineers said, there's always a third conductor, which is the outer skin of the coax. But if you're doing things right, you're terminating things right, you don't have any field that gets away from the coax. It's flexible. Okay. You can bend it in almost any way you want. in any plane. So it's quite flexible. It's also flexible for its in the way it's used. It's quite durable, and it's very easy to handle once you get the connectors on it. Some of the connectors are a little difficult to get on, but once they're connected, they're very easy to use. Next. Oh, some points on disadvantages of double line or twin lead connectors or parallel connectors. You can't twist them because that changes the impedance. If you take them and you rotate them through space that way, it changes the characteristic impedance of that cable. You can't run them up against a metal wall, despite what your friend out in California says, because it will induce current into the wall, and that's losses that don't get to the antenna.
Talking about twin lead now.
Twin lead, yes. And you can't bend it the hard way. This way. You can only go, you can only go this way. So you have to make a twist and then go like that to make a transition, and that causes problems with it. So it's great for straight line. It's great if you don't worry about field. If you wonder why twin lead is always narrow, because the closer those conductors get, the less the field radiates away from it. You spread it out, the field gets larger, and also the inductance of the wire gets larger. So that's some of the things that are the disadvantages of twin lead. Also, when you make connections, it's usually always a twisted wire on each conductor. And when you make those connections, it's subject to, if there's flexing, that'll fail at that point. So you got to watch that, or you've got to support that twin lead. So they each have their place. The twin lead comes closer to the feed impedance of a lot of antennas, and you'll see antennas where they design it to feed with twin lead and not with coax. So they do have their place, but far and away for what we do, we probably see more application of coaxial cable these days than we do the twin lead. Next. Again, why coaxial cable? Some essential concepts to be understood. And the reason I got into this is because I was doing some studying on this, and I was looking at the ARRL publications. The antenna book, the handbooks, all talk about skin effect. Nobody talks about proximity effect. And proximity effect and skin effect are controlled by and demanded and defined by Maxwell's first equation. You can't get away from it. You got to have one and the other. And so it's very important, especially to the functioning of cables. So we'll look at that when we want to see what these mean for coaxial cable. Move up there, Frank. I've got 11 slides here that were generated by a finite element analysis program that I have available. It's a freebie. You could download, you could go look for it. And it's the kind of thing that, we engineers like to play with. I use something similar to this professionally at work. And it does finite element analysis and modeling for electromagnetic circuits, electrostatic circuits, heat flow, and current flow problems. The next 11 slides are graphical solutions to the topics of proximity effect and skin effect. And we'll try to get through them fairly quickly. Go ahead, Frank, hit them. Okay, here's skin effect. I could do a program or an article for the voice coil on this program. I don't want to talk too much about the program because I know Danielle's an engineer. I don't know how many other engineers are in here. She's probably seen or knows a bit about finite element analysis and stuff, but maybe the rest of you aren't interested, but I could write a report on it. What I've done is the first thing you do is draw your model. And in this case, the model is an annular tubular conductor with a 2 1/4 inch outside diameter by a 1/4 inch wall. The large closely spaced circles out at the other end are where we take care of boundary effects. You can't do a finite element model for an infinite space. So therefore you have to tell the program how the field's going to interact after it gets so far away from the conductor. So, and what I've done here is I've plotted current density, or the J field, the absolute value in this case of the J field, which is current density, and the units are mega amperes per square meter. So it's a lot of current. What we have here is a 25 ampere or a minus 25 amp current flowing into this tubular conductor here. And you can see that the color that is presented on the conductor is very near the top of the color chart at the right-hand side, and it is uniform in color. That means that the current density across that wall of that conductor is identical from the outside to the inside. That's at 60 hertz. Frank, let's move to the next one. Same deal here. 25 amperes, same conductor, only we've taken and multiplied by 9. So we've gone to 540 hertz. And now you start to see a change in color. Your current density at the inside of the tube is getting down in this region, whereas we're still up near the current densities on the outer end are pretty dense. They're still up in that 6.75 e to the minus 2 megaamps per meter squared. So you're starting to see the current crowd to the outside just in a 9 times change of the current of the frequency. Next one, Frank. That shows that the center of that magnified a little bit so you can see it. You can see the differences in color even better. Okay, next.
Right.
There we go. Okay. I've left some other information in here about the model. You can see that there's air on the inside. The material used for the conductor is indeed copper. And there's air on the outside of that, and that air goes all the way out to the boundary conditions on the model. And we still have 25 amperes. We've gone to 1620 hertz. We're not even at RF yet. RF starts at 9.6 kilohertz, according to the FCC. So we're still in audio frequency, and look what's happening. The current density, there's even less to the center. And even denser on the outside. Hit her again, Frank. I think I got another amplified picture on that one. Yeah. Okay, so you can see actually the red is already crowding into the black line that we drew the model with. Next. Now we're at RF. We're in the middle of the 80 meter band at 3.8 megahertz, and you can't see anything. There's absolutely no current flowing on the inside of that conductor. It's all crowded out to the edges. Hit it again. I think I've got another blow up. Yeah, I zoomed in on this. And you can see there your current is all on the end, on the outside surface, and nothing at all flowing on the inside. You're down at you're at that blue that is wherever there is no current density. Still the same 25 amperes. The only thing we've done from slide to slide to slide is change frequency. So, and we're starting to see discontinuities in the color around there. In real life, that wouldn't happen. The way the model works, you do triangular meshes, and you can't make that infinitesimally small. There's only so small that you could draw the triangles to do the meshing of the model. And so consequently, it sort of falls apart when you get into these crowded areas. But that would be a continuous current around there, and it would still be very high on the outside and less to the inside. Hit it again, Frank. I don't know where I put up. Yeah. Okay, you can see the red high density is still out near the surface, and as you come in toward the center, it fades away to nothing. Okay, right, next. All right. That was a round annular conductor. That was part of our coax. Now let's put a conductor in the center of that. And now we have a piece of coaxial cable, albeit not what you would normally run. The reason I picked these sizes is because if I were to try to model something like this, the program has a lot of trouble actually doing the drawing because the lines tend to get bigger than the dimensions on the cable. So I blew it up. The principle doesn't change because the conductor size has changed. So we still have our 2¼ inch by 1/4 wall outer conductor, and now we put a center conductor in with a 1/2 inch OD. We've got a negative 25 amperes still on the shield, and I've called the interconductor IC, and I've got 25 amperes on that. So we got outgoing current on one and in return current on the other. If I were to make them both the same, proximity effect would take over, and it would force the currents back to the inside because they'd be pushing away from one another if the polarities were the same. So I got to have one going and one coming the way you would normally have one on the antenna cable. So this is 60 hertz again. Notice that the density out in the outer conductor is low. It's in this region here. And the reason for that is because we have to spread that 25 amperes out over a larger area. So there's a little bit less out there, but you see the same color that we had before in the interior one. The density is way up at the top of the color chart, which is a very high density current, and it's uniform in the cross section from inside to outside. Here, Frank. All right, now we've gone to that same 540 hertz that we did before, and we start to see something interesting going on. Instead of the current getting deeper or the density getting larger on the outer conductor, outside of the outside conductor, it's now getting denser on the inside of the outer conductor. And the inner conductor is starting to show density towards its OD and less dense current on the inside. So we're moving to the outside diameter of the center conductor, and we're taking the current and we're forcing it back to the inside wall of the outer conductor. Hit her again, Frank. I think I might have an amplified picture of that. And there you can see it clearer. You're starting to see lower current density out here, higher current density in here, lower density in here, and higher densities out there. That is 540. Let's go to the 1620, I think is the next one. And you can see it even more dramatically. And again, we've zoomed in on it. I didn't have an animation on this one, but you can see that this is, you can't see it very well, the colors. There is a little bit of yellow out here. This is the inside diameter of the outer conductor, and this is the outside of the inner conductor. And you can see things are going toward the center of the conductor. The two currents are being pulled by proximity effect toward each other because they have opposite polarities. So they're getting pulled toward each other.
Could you go show that one more time for the folks out there in Zoom lane?
Okay, sure.
I don't know if they'll be able to see it or not.
No, yeah, I don't think they'll see it, but not much resolution.
No, there's not. Okay, sorry about that, Zoom folks.
I can post this on the website or wherever we put it on Tiny whatever, and you guys could all look at it. All right, next. Okay. This is the H field, which is the magnetic field, and we're back to the annular conductor without being a piece of coax. And what I've plotted is the vector plot. This is called post-processing. Once you turn the cranks and the finite element program provides you the solutions to the various differential equations that Mr. Maxwell has provided for us, The post-processing gives you the color graphs. You can plot vector plots. You can plot current densities through the cross sections. There's all kinds of things you can do to demonstrate the physics that's going on here in a graphical manner. So what we see here is the vector plot of the H field in the air between the outer conductor, which in this case is just the annular conductor, and the boundary conditions. And note that the field is very intense, close to the conductor, and it falls off to almost nothing when we get out to the boundary conditions. It's still there. It's the old pebble in the water that you talk about with wave deal. So that field is very intense, up close to the conductor, and fades away. Next stage, next slide. And this is the coax again. And as you can see, the area outside of the, in the air beyond the outer conductor, there's no flux out there. There's no magnetic field there in this case. And that is at 5 kilohertz. I did that one. I don't know why I did that at 5 kilohertz, but you can see that the field is all completely contained within the coax. That's another reason to use coax, and indeed it is the reason that coax was developed. A fellow by the name of Heaviside, a British physicist, patented this back shortly after they started playing around with the transatlantic telegraph cables. And they'd lay multiple cables down there and put these things side by side, and there would be any crosstalk between the various channels. In those days, you had to put down a piece of coax for each circuit that you wanted to go across. So you had a big bundle of coaxial cables that they would lay in the bottom. And these fields, they wouldn't crosstalk to talk to one another because the coax cable does this. This is proximity effect. And I'm very surprised that the ARRL in their manuals don't talk about it. But they don't. All right, next one. And there you can see that without a lot of tiny vectors, you're just 2 vectors shown in there. And let's see, okay, Frank, take her next. So let's talk a little bit about characteristic impedance. It's always been a mystery to me. How do you have cables of varying lengths with reactive components, that is X sub C and X sub L, have a relatively constant resistive impedance? Characteristic impedance is also known as surge impedance, and we'll see why in the next couple slides. And the mathematical character is Z sub 0. Okay. So let's consider the schematic up there. This is a model, a circuit model of any kind of a transmission line. Twin lead, coax, it would look the same. And basically what we have is, it's a bunch of unit lengths. We always like to talk about unit lengths and their inductance and their capacitance. When you go to a coaxial cable specification table, you'll see it has so many picofarads per foot of capacitance, and you'll see that it has so many millihenries or microhenries of inductance per foot. Okay, so each of those sections there, and I'll have that in another drawing drawn off to show these unit lengths. The inductors are the inherent series inductance of the wires, while the capacitors are the capacitance between the wires. Anytime you have 2 conductors separated by an insulator, you have a capacitor, and it's capable of storing electrostatic charge. The 6 unit lengths here are part of an infinitely long transmission line. They like to do this modeling with infinite lines. It has some convenient effects. They're not realistic, but it allows us to do things with the mathematics that makes things easy. Next. So here it is drawn again. I've added an energy source and a switch And you can see the green boxes are these, there's 6 of these unit lengths. Again, this is part of an infinitely long transmission cable. And the reason we talk about that infinite, there is no end when it's infinite. So there can't be any reflection, because you don't get reflection until your signal gets down to the end of the line. Okay. Now, where it becomes usable for a real world situation is that if you terminate that line in a resistive load that is equivalent of Z0, 50 ohms, for example, or 72 ohms, all of your power goes down that line. It gets absorbed by that resistor, and there's nothing that reflects back. And hence, again, what does it look like? An infinitely long line. Mathematically, it becomes an infinitely long line again. So very good to do that. So what happens if we close that switch? Frank, hit it. Your signal propagates down the line a lot faster than this, of course. It happens at damn near the speed of light. But for the sake of looking at this, you see each section charges. The capacitors charge with a voltage. The inductors come up over a period of time to the allowable current that's specified by the voltage that's providing that. And it propagates down the line. That's your surge. When you first close that, you got current and voltage up here, and nothing is happening down there. But at some time in the future, very short, picoseconds, microseconds, femtoseconds, something like that, you get the voltage ends up at the other end, and the current finds its way down to the other end of the line too. So this is why they call the ZO surge impedance, or characteristic impedance, okay? Go ahead. So this is there again. I'll repeat: the infinite line has no end. There cannot be any reflectance. It's convenient for mathematical analysis purposes, and the math is pretty heavy with this stuff. A finite length with the specific ZO looks infinitely long when it is terminated in an equal Z0. The matching load, as I said, absorbs all of the power in that when you have that case. Next. Strangely enough, ZO is known to be resistive. How is that possible? Now, in these equations here, the L is the inductance per unit length of the coax from the model and from the spec tables for the coax. R is the unit length resistance of a finite length, or the specified unit length, which is usually a foot, by the way. We talk about antenna lengths and meters and stuff like that, but when you see these specifications in the coax table, it's ohms per foot, capacitance per foot, and inductance per foot, usually. So don't know why there's that dichotomy there, but there is. G is the conductance in Siemens of the, and that's the SI units for conductance of the dielectric or insulating material between the conductors. So all of this rigorous mathematics with the differential equations and so forth. Those of you have seen textbooks where the math comes down and there's all this stuff. And from the above, any fool can plainly see that the following is true. And there's a linear equation down at the bottom of the list. We've all seen those textbooks. Well, that's the same thing. I'm not going to go through that math. Some of it's above my pay grade. I went through it and tried to understand quite a bit of it. And I got through most of it. And I said, yeah, I'm not talking about that. So next. But how? Click. We want to focus our time on this side of the equation and over there. We're not going to go too much over here. We're not going to talk about the left-hand side of that all except ZO. So we'll go to the next slide and we'll analyze what goes on. Click. No, those were in white. It won't happen.
Well, I'm using LibreOffice.
Oh, shoot. Okay. Well, what I have is a situation up here. That dot shouldn't be there. Hell, this is not good, Frank.
What do we got? So
Okay.
it's not showing the full equation, is what you're saying?
Yeah, you see the parentheses and the dividing lines, and that's the heart of this thing. You've got a situation, I think, on the top where you got 1 minus R over omega L. And in the bottom, you'll have a G over omega L. R and G in that unit length are very, very tiny numbers. And as the frequency that you're applying to this goes up, omega L and omega C are on in the denominators of those two fractions that you see with nothing in them. What happens is that side of the thing under the radical starts to go towards zero. And as you get closer and closer to zero, the right side or the left side of the radical gets to a 1 minus 0 divided by a 1 minus 0. And hit her again. Yeah, it's not going to show you that. And what happens is the imaginary portion or the unreal portion of the equation goes poof. It goes away. And what we're left with is ZO is approximately equal to the square root of L over C. Hit her again. And so to maintain equality, if the stuff under the radical is real, therefore ZO, or characteristic impedance, must be real. And it is. It's a resistance. And that's how you analyze how this comes down. I don't know whether it helps anybody, but it turned a lot of little lights on in my head. Oh, this is how it's possible. This is how you have a resistive impedance. And I've changed the sign there from an exact equal sign to an approximately equal sign because I said that these two terms up here approach zero. In the real world, they can't get to zero, but they get damn close. And so you got 1 minus, so the other side of that thing comes like 0.9999998 divided by 0.9999998, and the square root of that is 1. And so that becomes 1 times the square root of L over C, which was what was in here. This was the square root of L over C in there. And that's what happens. That's how the thing becomes a real resistance. So it's been a mystery to me for all these years, even as an engineer, because I didn't study this stuff because I worked in different areas, but and as a ham, it's always, and that's how. Next. It's also defined that ZO turns out to be the ratio between the peak voltage and the peak current of that surge that goes down the line. And a couple interesting things happen because of the previous slide. So what do you have when you have resistance divided by current? What do you come up with? I'm sorry, voltage divided by current. What do you come up with? Resistance. So it makes sense that ZO is a resistor. The other thing that happens, seeing as ZO is real, and if you terminate in a pure resistance at the other end of the line, guess what happens to the current and the voltage in that surge? Dave? Sure where you're headed. What happens to what's the phase relationship?
In a resistance,
Yeah,
there's no phase change.
there's no phase change. So when that pulse goes down the line, the voltage and the current, if there is no reflection, if you're looking at something that where the whole lump is Z0, when it goes down the line, the voltage and the current are in phase. And so you can easily calculate the real power going down the line with that. Okay. We're back to this again. I said we want to remember that. So how do you set up ZO? What dictates what the ZO is or Z0 is of a cable? Well, that equation up there says that ZO is solely dependent on mechanical and physical electrical properties. And I've changed that to a capital D in my, there should have been an equation there somewhere, but that's all right. So I got a capital D, whereas that's D1 in the diagram is the inside diameter of the outer conductor, as we mentioned before. And the other case, we've got the outside diameter of the of the center conductor. And K is something called the dielectric constant or permittivity. And that is the measure of how good of a insulator the foam or whatever it is there between the inner and outer shield is. That value is 1 for air, conveniently so. And for the typical things that we use, that we find in commercially available coax, it gets up to about 1.8, 1.5, 2. There are some really neat stuff, but you don't see that in coax that we buy. They get up as high as 4. But so hit the slide there, Frank. Let's see where we're going to go from here. Nope. So let's look at the velocity factor, bending radius, and UV resistance in the direct barrel. We could take this home. As we know, propagating through a vacuum, radio signal propagate at the speed of light. When you put them into something other than a vacuum, when they have to go through real world materials, they slow down. They're not quite as quick when they go through other mediums. And the difference between the two speeds expressed as a percentage is something called the velocity factor. And again, we can't see my equations. And basically, it's 1 over the square root of K, that little K that we saw, or which is dielectric constant, or it's 1 over the square root of epsilon, the lowercase Greek letter epsilon, which is the same deal. It's they call it the permittivity, and it's one's old school, one's new school. The dielectric constant is old school. If you're looking at old textbooks, you'll see the K. You're looking at modern stuff, you'll see it described as permittivity. And that basically says how much current does the insulator permit to go from the outer conductor to the inner conductor or back and forth. And you want that to not be a very good deal. You want that to be a good insulator. So, so that from the above, it would appear that the shunt capacitance is the primary controller for velocity. So the capacitance between the two conductors, because the voltage can't change instantaneously in a capacitor, and you can make the capacitor fairly large, that's what sets the velocity factor. 1 over the square root of epsilon or 1 over the square root of K is the velocity factor. You'll get a fraction, you multiply it by 100, and there's your percentage. When you go and you look at a catalog, coaxial cables come with a bending radius specification. And that last equation we looked at that states what the characteristic impedance is quite important to what happens to a piece of coax if you abuse it and you do something like that to it. What do you think has happened at that point? Anybody want to?
Physically,
The shield can get broken.
You
Anything else?
physically changed it.
Diameter and change over conductor.
You're gonna get a change over diameter. It's not gonna be round, it's gonna be elliptical. When I do this, what happens to the dielectric material at the top of the bend? It's forced out, it stretches. What happens to the dielectric material? And it gets thinner then. What happens to the dielectric material on the inside of the bend?
Compressed.
It gets compressed. So it forces the interconductor up this way and gets it into closer to this, to the outer conductor. And at this point in time, then, even when you straighten it out, guess what happens? What's the characteristic impedance in here? Is it 50 ohms anymore? Nope. God knows what it is. I wouldn't want to try to calculate it, but that's what happens when you do this. That's why they specify the minimum bending radius. So, you know, when you slam this in a trunk on an antenna mount, you've got a bump back there where that's going up to your antenna. So if you get a permanent distortion in a cable, they get a permanent impedance bump at the point where you've done that. You run it over with a truck or a car, you catch it with something that puts a force at the center, a real strong force at the center of it and changes that geometry, you change the characteristic impedance. Next, Frank. You want to buy coaxial cable that has the outer jacket that withstands UV. You don't want, because you're going to be using it outside, if it's up on the top, you're burying it, that's one thing. If it's going up the tower, or if it's going up to feed the center leg of a dipole or something, it's out in the sunlight and the sunshine. And if it's not UV resistance, it's going to decay. It's going to start to, I've even seen this stuff start to leach. And what happens is decomposed plastic gets into the braid, gets in, contaminates the inside insulator as well. And guess what that does? Remember the dielectric constant? It changes it. So what does that do to ZO? Makes a change to it. So you want good quality cable that has a UV resistant outside jacket. And finally, I don't know if I have a slide on burial. I once made the question, I said, when you say direct burial, because you print that directly on the outside of your RG8X cable and your others, there's a local vendor that we all know and love, or some of us know and love, and some of us have a love-hate relationship with. But it's a big, well-known name of ham equipment in the local area. I once asked one of their guys, I said, so when you say direct burial, do you mean it? And he said, absolutely. He says, you can do that. They recommend you go below the frost line, but you can direct bury this stuff and you're good to go. And I said, well, what about protecting it from shovels and stuff like that and so forth? He says, well, you go down below the frost line, you pretty much don't have to worry about that. But if you're not that deep and you want to run it through a piece of conduit, just make sure that whatever conduit you have it run through has holes in the bottom of it so it can drain. Because underground, you think, oh yeah, it's got it, you know, I've got everything sealed up. It's not going to get any water in there. If it's open to the atmosphere, you will get water in it. You will get condensation. The humidity will change down that line. You'll get condensation. And if you can't drain out of the bottom of the cable, you will get water impinging on this. You'll cause the outer conductor to corrode, which changes the resistance and the inductance of the outer conductor. Eventually, it'll find its way in between things because of capillary action. And then you change ZO again. And you get all kinds of losses and so forth, and it doesn't act the way it's supposed to. So the idea is if you're going to direct bury and you're going to put it in some protection, make sure that you've got drainage out of that. Drill holes in the bottom and make sure those holes go to the bottom of the conduit. Also, you're going to go, and if you're careful and you're any decent at construction, you'll lay that in there so it's a perfectly level stretch, and you'll bury it back up. And guess what happens in 2 years? It's not level anymore. It groundless. So your nice flat piece of conduit that went out there that you figure, oh, it's gonna be flat, it's not gonna collect any water in low spots. Guess what? There will be low spots, it will collect water. Guaranteed. So, that's what you wanna do with the coaxial cable. If you're gonna use a direct burial, bury it. Maybe you wanna throw, play sand or something in the bottom of the trench. And then maybe cover it over with a little bit of play sand, so it's got stuff that could move. And then just cover it over with the grass grow over it. I'm lazy. I found out that I can lay this right on the top of the soil, and within about 6 weeks, it's down below the level, and in 2 years' time, I've got that much soil over it. It buries itself. Now, there's no protection for somebody coming and sticking a spade in the lawn and cutting through it. But I try to remember where I put it. And when I'm digging, I try to determine that I'm not digging into it. So that's direct burial, and that's next slide, correct? That's it. Questions? Tanner?
You said there are, some people may not know, what is the depth of the frost line around it?
3 foot.
3 foot is good, I think. 18 inches at minimum. Pardon? 42 inches? Does that compensate for global warming? It's probably shallower.
So in other words, if you go down about a foot or so, you're probably still good around here as long as you don't stick it with a shovel.
Right, yeah. Yeah,
Because most people aren't gonna bury their coax 3 feet in the ground.
no. Although I know some, there's a guy here in the room that probably does. Wes probably goes, he probably buries it that deep. Yeah.
Not so much a question, but an experience. I went out to a fellow's house, he had the, big old, ugly dish, the 10-foot dish. Had the ribbon cable going out to it. And he had a new house and he had it put into, the conduit, like he said, with a PVC pipe. And he had it coming right off the top of the PVC pipe, and go way down in it. And then an elbow, then down into the house there. And it filled up with water and it froze up and actually crushed the cable from the ice.
Yeah.
Direct buried the new ribbon.
I know a fellow that buried a coaxial cable and groundhogs.
Yeah,
They picked up.
yeah, that's a possibility too. I've got groundhogs in the neighborhood, but I've been lucky. They've never attacked my cables. I had a contractor to rebuild a deck for me to attack one. When I marked it, it says, don't dig here. He dug there.
I think he's paying for the new coax.
He probably should have, but I didn't discover it until several weeks later. How come this antenna won't?
When you go use your radio, you had SWR 5.
Yeah. Yeah. I turned the radio on, there were no signals there. I said, well, I went out and I got the propagation tables and I looked at that. Gee, it should be good. I went to spaceweather.com and I said, nothing here. It could be causing, we should have good propagation. I can't hear crap. Put it tried to tuner, it couldn't find anything. And I said, I bet you they got my cable. And I went out and dug it up, and sure enough, it was cut in half. There was a shovel that wouldn't have gone through it. David,
I've been saving up questions for you.
I bet you have.
Yeah, so I'm gonna go in reverse order here. We talked about bending radius and you referenced, looking up the specs.
Mhm.
Is there like a rule of thumb or anything for that?
No,
Okay,
it's based on the materials, just like everything else. It's based on the material that's in the cable and the diameter. And you have to go to the manufacturer, you have to look up the cable that you're interested in. And sometimes you can find the information, sometimes you can't. But if it's like Belden cable, you go to the Belden website, you could look it up. And you'll find that there's a different bending radius for each size.
Huh.
I didn't do any math to analyze whether there's any correlation as you change sizes or anything like that. But I think it depends on, sometimes you get a coaxial cable that doesn't have a solid foam. But you've got spiral spiders that run through there, and it's a combination of air and, this is expensive cable that you see this with. Air and the dielectric material. And that's a different game than something with a solid foam. Because if you displace that spider, or that spiral wrap in there, it's, you know, it does the same thing that this does. And it's a different animal, so those will probably not have the same bending radius that a comparable diameter cable that has solid foam would have.
Another issue, if you take a look at LMR 400 right now, there's two variants everybody sells. There's the stuff with the solid center conductor, and there's the stuff with the, what do they call it?
Solid?
No,
PTFE?
no, the solid center conductor,
Oh,
and then a
stranded conductor.
stranded, thank
Center
you,
conductor, yeah.
stranded center conductor. And the stranded center conductor, they call Ultraflex because it's got a much smaller diameter minimum turning radius, okay?
Yeah.
Whereas the solid conductor is a much larger turning radius. And it's because the center conductor of obviously stranded will flex.
More,
Yeah.
right. So you don't have as much mechanical stress from that center conductor on the insulating material around it as you would when you had the solid one. The solid one's gonna put more resistance to you bending it, and it's gonna put more force against that insulation. Go.
Dave,
Yeah, Andy, typically a coax we sell is like 6-inch bending rate.
Right.
Some of it is different.
Mm-hmm.
And what we look at is stuff that flexed a lot. Like if you're gonna have a rotor. or something,
Rotor, yeah.
We found that some of the softer dielectrics, the center conductor will migrate.
Mm-hmm.
So we like to have a solid conductor up on the motor, such as an RG 213
Mm-hmm.
has a solid conductor.
With a loop so that you've got
Right.
play in it.
So
You put a loop up there at your rotor, and when it goes around, it doesn't stress the cable as much. And you're guaranteed that you stay away from whatever their bending radius is. Yeah, DX Engineering, if you want specs on that, you can get the specs from them pretty well.
I have probably about 800 feet of RG6/U. Swept out the 3 gigahertz meant for a satellite industry. And my question of it is a 75 ohm cable. And I use or make a balun to go and go from 50 to 75 and then that.
Yeah, you can tune that out. So it looks like 50 ohms here and 50 ohms at your antenna. There's ways of doing that.
Have you ever seen any sources
Pardon?
of such?
I've never had a cause to look because I don't have a spool of RG6 sitting in my garage, so I've never chased it, but yeah, you can do that.
This network installed for 20-something years.
Yeah, coax can be used as, and I didn't discuss that here because that wasn't the area that I wanted to get into. But coax can be used for impedance transformation. So, yeah, you can do that.
just a quick story on one topic that Andy touched on, exposure and shields and things like that. At YSU, in the original station that was put together back in the mid-90s by Norm Into, there was a good, long, 150, 200-foot chunk of RG8, I think it is, which is, the good half-inch size cable, good industrial cable, going out from the shack along the roof of the engineering science building all the way out to an antenna, okay, long run of coax. And that antenna fell down, got destroyed in the wind, et cetera, et cetera. And we built a new antenna that had a different feed point, and we had to move that coax. As it turns out, long story short, the connector on the end of the coax, we took a close look at it and went, this isn't in too good a shape. Clipped it off to put a new connector on the end of that coax, right? We go to strip the outer insulation off the coax, and the outer conductor just went like dust in my hand, okay? Okay, we had some weathering in this coax. This is not good. Let's go back a few feet or a foot and clip it again, and we'll be able to solder, right? I had to take 3.5 foot off the end of that coax before I got to any kind of shield, and the shield I got to was still questionable, okay? Now, what's the moral to the story? It was good quality coax. It's sitting on a hot, black asphalt roof. Think about how you'd be after a few years of that environment, okay? And the long story short is that shield has probably completely decomposed, even though it's still inside physically of that outer insulator, okay? We're gonna have to replace that whole line. And that's been up there 20 years, which is, things go, that's not an awfully long time, but under really adverse conditions, this stuff doesn't last forever.
And I bet you that along that entire length, the per unit R resistance of that shield is nowhere near what it was specified to be when that thing came off the reel. Out of the factory.
Even if that shield's still all there.
Yeah,
The real problem was the end of that connector was leaking water down into that coax. It will travel.
Oh, yeah, 'cause
way
it-
down in there, like,
capillary action, just like a sponge, takes it all the way down.
I've had that happen, to satellite ones. We use 18 volts DC between the center and the shield, and oftentimes I open up an F connector to find the center, just a piece of rust that was gone. That's what Phil advised the people who called me, I don't have any satellites here. So we pull that out and strip back so far and say, okay, finally I get that clean center and clean out of the shield, and I can use it and replace it.
I think Dave's got one or two more, or do you?
Oh, I think I could probably come up with one. What I have here. Oh, yeah, when you were talking about the guy that developed the coax overseas,
Yeah, actually, he patented it. Somebody else developed it. And he studied it and determined how it would work, and he stole the patent.
did you come across,
Heaviside,
did you come across what the application was they were doing that for?
transatlantic cable, for
Okay.
the first CW cables that went in the 1860s, 1870s across the Atlantic.
Okay, UHF connector versus N connectors.
Yeah,
When do I need to go to like an N connector? When will UHF?
when you want a 50 ohm connection,
Yeah,
use the N connector.
okay,
If you don't mind a slight impedance bump at the connection point, and the frequencies are low enough that it's not gonna hurt you all that much, then you could use the
UHF.
UHF connector. And I was going to do an analysis on that with the program, with the finite element analysis, to find out which end of that connector really isn't 50 ohms. Because there's not much of a change in the physical dimensions on the male end. But the female end sure in hell looks a lot different than this. So I was gonna do an analysis on that. I haven't done that yet. This is something to look at with the finite element program and see if that can tell me where the impedance change is. But the N connector's a better connector. It's greater over a wider range of frequency, costs more, but it gives you a 50 ohm connection.
BNC is actually a better.
And BNC does the same thing. BNC is purely 50 ohms.
Huh.
It gives you a connection that way. It doesn't handle the power that the N will.
No, that's not true.
will?
BNC connectors, the power rating is solely rated on the coax that's in it.
Oh,
Okay.
really?
I was curious
Didn't know
about,
that.
yeah, I went through this whole metamorphosis of moving from soldered coax connectors to crimp-on. Years ago, I was totally against crimp-on connectors. I'm the other way now completely, okay? But in that journey, I looked at all these different types of connectors, and really an N connector is really a BNC with a larger outer to accept the bigger coax.
Mhm.
And that's the only difference between an N connector. If you take a look at an N connector, it's just a modified BNC connector.
Yeah. You look at the inside of it.
Yeah,
it's
the
same.
BNC connector is actually good to almost 2 kilowatts.
Hmm.
With the proper coax, That's the caveat. You use crap coax because it's a smaller diameter to fit the connector. You use crap coax, you don't have the same power. But the BNC is actually superior to even the N connector as far as frequency response. An N
Mhm,
connector
yeah.
is good up into the gigahertz.
That's why you find it on instruments, why you find BNC connectors on instruments.
Yeah.
Signal generators, VNAs, well, you'll see a lot of N connectors on VNAs too, but, scopes,
Not what a VNA is, Andy.
vector network analyzer.
There you go.
But the BNC actually out of the three is the best connector. Nobody uses them. David?
And typically what we see, we recommend like up to 2 meters, you can use the PLC 59.
Yeah,
Above that, you want to use.
you know, but use the N.
Typically what you see on some of the transits.
Right.
2 meters would be a PLC 59 one. That's like 239, and then 440 shows up as an N.
Shows up as an N conductor, N connector. And that's because the N gives you that wider range of frequencies.
You're an hour.
I'm done. Unless Dave has one more
No,
question.
I'm good.
You're good?
I'm good.
All righty, gang, I hope that helped a little bit, and it answered a couple mysteries that I've had. Okay?
Go ahead and kill the recording.
You get that.